Hello everyone, I am Hamida Mohammed Lamin from Algeria. I am an assistant professor at the University of Tizi Ouzou. First, we'd like to express our gratitude to Prince Sultan University for providing us with the opportunity to participate in this conference. For Professor Ahmed Taher Azhar, the leader of the automated systems and soft computing labs, deserves special recognition for his assistance, and it is our pleasure to be part of this research lab as international collaborator. Today, I am going to present our work, Fuzzy Logic Cyclic Report Modulation Control for a 5-cell inverter. So to do this, we have choose the following plan. In the introduction, I will talk about the studied converter, and I will give some advantages of this structure. The average model of the 5-cell inverter will be given in the first section. Then I will present the principle of the modification cyclic reports control strategy. In the third section, we will design the fuzzy logic regulator using to control the load current of the converter. And in the fourth section, we will discuss some simulation results. And we will finish with a conclusion. So with the development of power electronics converter technology, a new structure are appeared. Among this structure, multicellular converters are based on the Cyrus association of elementary switching cells. This converter have two major advantages. The first one is the distribution of voltage and current constraints under power switches. The second one are the spectral qualities that present the output voltage. We see in this figure 1, the topology of the 5-cell inverter who is connected with an oral load. The major problematic of this topology is the destabilization of the capacitor voltage. Here we have 4 capacitors, so we have to regulate 4 voltages, VC1, 2, 3 and VC4. The voltage across these capacitors should be maintained at the references given by the expression 1. The mathematical model, this is the average model of the 5-cell inverter, is given by the system of equation 2. Here we can see the representation of the control scheme. The principle of the modification cyclic report control is based on the modification of the cyclic reports. So when this duty cycle are equal, so the capacitor's voltage error will be equal to 0. We have to note that this control ensures only the regulation of the capacitor voltage. In our study, we have proposed a fuzzy logic controller in order to regulate also the load current. So the output of this regulator will be the cyclic will be the reference value of the duty cycle. Equation 3 gives us the expression of the variation of the capacitor voltage. We can express the current the capacitor current by the equation 4. Now we replace the equation 4 in the equation 3. We get the new expression of the variation of the capacitor voltage. MK here represents the difference between the adjacent rapport cycle, sorry. Then you get the new expression of the MK. To avoid cyclic rapport saturation and to provide a significant balance dynamic in the first phase, we introduce the gain G. Of course, we have to take into consideration the load current, who is sinusoidal in our case. So we add the function sin to the load current. The gain G may be calculated using the formula given by expression 8. After development, we get the set of equations below. This is the control law of our converter. In this slide, we will give the internal structure of the developed fuzzy logic, where the inputs of our controller is or are the error and the variation of error of load current, and the output will be the new the new input systems. The gain GP here is added in order to improve the transient time. The membership inputs of the proposed controller are given in the slide. We can see also the membership of the output. Here the table of the fuzzy rules. Now we'll show some simulation results. We have made a simulation using MATLAB Simulink software according to the following parameters. Figure 4 shows the evolution of the floating voltage under our control. We can see that the capacitor voltage quickly converges to their reference value. Figure 5 illustrates the progressing of the load current and the output voltage. It's clear that both are in phase with the same frequency, and the load current exactly matches its reference. The proposed control performance is compared to the traditional P and PWM noted balancing. You have obtained the result given by the figure 6. So when compared to the standard PE regulator, the suggested fuzzy logic controller ensures a good convergence of the load current to its reference. Furthermore, this controller reduces the shattering inducing by the natural balance strategy. The load currents FFT harmonics spectrum are given by the figure 7. We can see that the THD is reduced, HD is reduced to 0.38% by the proposed controllers, whereas THD is equal to 0.41% and 0.93% by the standard PE regulator and material balance technique respectively. Figure 8 demonstrates the controller's effectiveness when the input voltage is varied. So the suggested controllers and the traditional PE regulator allow the capacitor voltage to be converged to its new reference in a short time and eliminate the ripples. The zoom confirms that the fuzzy logic controller reacts first. The figure B demonstrates that the natural balance control requires more time to achieve this convergence and results in ripples. To demonstrate the robustness of the control laws, the value of the load resistance will fluctuate to minus 19%. Utilizing fuzzy logic and PE regulator uh, has not effect on the capacitor voltage or output current. However, it can be observed that the natural balance control is not robust in the event of parameter fluctuation. As conclusions, the control law ensures a good regulation of the load current and the floating voltage. We have observed a minimum response time, and the proposed algorithm minimizes the ripples of the capacitor voltage and improves the quality of the output current. I am coming to the end of my presentations and thank you for your attention.